Okay, today we derived the Reynolds transport theorem, and I'm certainly not going to go through that whole derivation again here, but I just want to remind you of the basic pieces of it and then show you the key results. So here we have a flow in a conduit that is going from left to right in the same way that I set it up in class. And we have a control volume, which I'll show in red. I have different colors now, so I can show a little bit more clearly. Control volume in red, and a system which at time 0 matches the control volume. So here's our system at time 0. At some later time delta t, this control volume, the system has moved some distance, and I'll show with a dashed line where it sits at a later time. So this is at t plus delta t, t0, at t0 plus delta t. And I guess to make it real clear, maybe I can put that in green and show that system at that later time. So what we have is some fluid that has left our control volume. This is our flux out. And we've have some fluid that has entered our control volume. That's our flux in. The Reynolds transport theorem is really just about accounting for those fluxes when we're writing down our conservation laws. So for a quantity B, whatever that might be, it could be mass, momentum, energy, we can say that the time rate of change of B for our system is equal to the time rate of change of B for our control volume, plus accounting for those fluxes in and those fluxes out. And those fluxes in and out are going to be related to the velocity that's crossing the control volume. And so we can write that as, I'll do it as the sum of rho beta, I'll do it as plus or minus VI AI here, where plus is for outflows and minus is for inflows. And that accounts for the fact that one is the flux out and one is the flux in. Now in class, we talked about different forms of this equation, specifically focusing on this last term for cases where we could write it as using vector notation, or where velocity might vary and we have to do it as an integral. But in aggregate, the conceptual aspects of the Reynolds transport theorem are consistent across each of these. The time rate of change of what's happening for a system of particles that we could follow is described by the time rate of change of what's happening in a fixed volume or Eulerian frame, as long as we account for the fluxes in and out.